So we may have this in our notes already from last time, but today, or in this particular section, we're planning to discuss parametric equations and some calculus involving parametric equations. So some of the calculus that we've done and talked about, when I say us and done and talked about, I mean from your Calc 1 and Calc 2 courses, tangent lines, areas under the curve or within parametric curves, and arc lengths. So those should be topics that you're familiar with. Now we're going to look at them from the context of a parametric equation. So I think we did an example already with the tangent line, but here's the formula for the second derivative. So when we're taking the second derivative, remember that the parametric equations are functions of t. They're x of t and y of t. And so because they're functions of t, when you put them in the context of a curve, a graph, you're looking at dy dx when you're finding the tangent line, for example. Or if you remember back in your Taylor polynomial days, you can find a tangent parabola as well. The second degree or second order polynomial that's closest to the curve, and that uses your second derivative, so this is your second derivative. Now the second derivative isn't just the second derivative of y divided by the second derivative of x with respect to t, because that is with respect to t. So you want the second derivative with respect to x, and that is going to be a little bit different. But in general, this is how you can think about the derivative. So the second derivative involves you taking the derivative of the first derivative and that's what's going to go in the numerator, and then you're going to divide by the derivative of your x function. So let's go ahead and do a problem. And usually for examples of problems, I usually just like to dig from the exercises in the textbook. And I copied some of those here. Kind of hard to see, but let's see if we can blow it up a little bit. And let's pick a problem. 3, 4, 5, or 6. Just throw out a number. Doesn't really matter. 3. Let's do 3. We have parametric equations. X is equal to quadratic, 1 plus 4t minus t squared, and y is a cubic function. Y is equal to 2 minus t cubed. It says find an equation of the tangent line to the curve at the point corresponding to the given parameters. All right. So first thing we need for an equation of a line, or one of the two things that we need for an equation of a line is the slope. And for the slope, we need the derivative. So let's say that we're looking for the slope. And then we're going to need a point. We don't quite have a point. We'll talk about that point in a minute. But we need a slope and a point. So let's find a slope. And for that, let's just take a quick peek again at our derivative formula. The derivative dy dx is pretty simple. It's dy dt over dx dt. So it looks like we just need dy dt dx dt. So I'm going to shortcut it to just use a prime notation. This is going to be the numerator, y prime. And y is a function of t, so let's assume maybe I should put this as a function of t just to be clearer. And the derivative of this is just, what is it? Negative 3t squared, right? So that's going to go in my numerator. My denominator is going to be x prime of t And this is going to be 4 minus 2t. So remember that when you did this in Calc 1, when you find a derivative, you don't just put that thing into as a slope, because that whole expression is an expression for the derivative at any x or t. In this case, it's for different values of t. So you want to take the t that they give you and evaluate it at that point. So dy dx is equal to, this is in general, is equal to the y prime over the x prime. But this is not the slope that you want yet. And the thing that you need to do is you need to get this a slope, you need to identify that this is a slope at t is equal to 1, because that's a specific value that you want. So for this, you're going to put 1 in for t. So negative 3 times 1 squared, 4 minus 2 times 1, and this is going to give me what? Negative 3 over 2. Okay, got my slope. So now I want a point. So they gave me a t value, but when I'm looking at a point on an xy plane, I'm looking at an x and a y value. So when t is equal to 1, your x is equal to, let's put 1 in for x. Maybe this notation would help. This is saying 1 in for t, sorry. Let's put 1 in for t in your x value. I think that's 4. And then your y value, when you put 1 in for t, is 1, 2, 1. So 4 comma 1 is your point. So let's write the equation. So the equation of the tangent line, let's see, I can go that y minus y1 business, but I'm going to write the equation a little bit differently. I say y is equal to, and this is a formula. What's the formula? This is probably not the best way to do this, but I'm going to write it anyways, because I want us to think back to Taylor polynomials. F of x, or f of a, plus f prime of a, x minus a. You should try to convince yourself that this is the equation of a tangent line. And then if you want to, this is your y1, this is your slope, m, this is your x1. So we got our y1, x1, and our slope, so we can easily write that down. Your equation y is equal to 1 plus, let's say, negative 3/2 x minus x1, which is 4. All right? You can simplify this if you want, and then it should be easy enough. It's just simple algebra to simplify. But this is the equation. All right? Okay, now I want to extend this problem. This problem is just asking for the equation of the tangent line, but I want to extend this to also look at the second derivative and then try to make our tangent parabola. Have you guys ever heard of tangent parabola? No. No? Okay. let's see if this looks familiar. Let's call it P2 of x is equal to f of a plus f prime of a x minus a plus f double prime of a over 2 x minus a squared. So this is the beginning of a Taylor series. If you stop your Taylor series at 1 at the first derivative, you have the tangent line. If you stop your Taylor series at 2, you have a second order polynomial, a parabola, quadratic. You have a parabola that is, and I'll say in quotes, tangent to your graph. And so, and then if you go further to the third derivative, fourth derivative, etc., then you're going to continue to have your polynomial look like your graph, whatever the graph of the line is. So the first part, the linear part, is already done. And so if I want to find your tangent parabola in this case, I would just need the second derivative. So this would be an excuse for us to use a formula to find the second derivative. So let's find a second derivative. D squared y over dx squared is our formula for the second derivative. Now remember that the functions are functions of t, but we want the second derivative of y with respect to x. So according to the formula, and I'm going to take a peek again at the formula. According to the formula, I want the derivative of the first derivative with respect to x. But remember, it's a t. So let's look at this last formula over here, or last part of the formula. It looks like I want to take the derivative of dy dx, and I want to divide by dx dt. Okay, we have dy dx, right? We just did that on the previous problem, and then we just need dx dt. So why don't we just, for good measure, take a quick picture of this and bring it to our next slide. This is the formula that we're looking at to get this thing. Maybe I'll put it over here. So I want the dy dx. This is my dy dx right here, right, as a function of t. I want the derivative of this on my numerator, and I want the derivative of dx, or I want the derivative of x with respect to t. Wait, I already did that, right? That one should be easy. What's dx dt? We did that already. That's 4 minus 2t. The ddt of dy dx is the derivative of this thing with respect to t. Looks like I'm going to have to use a quotient rule. So how's the quotient rule go? Low, d high, high, d low, 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 d high, high, d ho, ho, ho. So looks like it's the low, 4 minus 2t, d high, minus 6t, out of room, minus high, d low, that's just negative 2, all over 4 minus 2t squared. If you can find a way to simplify that, that would be great. Or if you want to be brave and just drop a 1 in there, which is what we need to do, because because we want to evaluate this at 1, then you can go ahead and do that too. Anyways, can somebody just tell me what the answer is so I don't have to do it? Negative 12 for everything, or just the numerator? Yep. Okay. The numerator of the numerator, or the whole numerator? Numerator. So negative 12 divided by, this one was 2, wasn't it? Yeah. Over 2. So negative 3. Can we get a confirmation on that? Jesus and I were just throwing this around. Oh, so this is going to be squared. So 3 over 2 again. Don't look at my work. Do it yourself and then let me know if it's right. Is it too dark? Should we turn the lights on? All right, I need 2 people to say it's correct, and then we can move on. Anybody? Yeah? Woo. One more. Confirm. Let's confirm this. It's not exactly a consensus, but I figured if 2 people got the same answer, it might be correct. Yeah. Yes. All right. So we got our slope, or not our slope, we got our second derivative, so we just divide that by 2 and then put that into the formula and we get our, quote, tangent parabola. So tangent parabola is going to be, what's it going to be? Basically this first part over here, 1 minus 3/2 x minus 4 plus minus 3/2 over 2, let's just call it minus 3/4 x minus 4 squared. Okay. So I always like to visualize or be able to visualize things. So I got an easy graphing program here. I'm going to graph the parametric equations, and then I'll graph the tangent line to make sure it's tangent. And then I'll graph the other point, make sure, or the other graph, the tangent parabola, to see how it would look like. So let's give it a shot. You could do this in your calculators, but the calculator now, if you do this on your handheld calculator, you have a graph that is a parametric equation, but then you have to graph a couple of other graphs that are not parametric equations. You can make it into a parametric equation, but I'll tell you how you do that in a minute. But I have an easy grapher, so I'm just going to use this one. So to graph parametric equations in my little graphing program, I make these things called vectors and fill it up with whatever those functions are. So the x is 1 plus 4t minus t squared. This is a t. And then the y is 2 minus t cubed. And right now I have this graphing from 0 to 1. So if I'm interested in a little bit more, maybe I'll go from -2 to 2. So let's just say it looks like that. I want to be at the point when t is equal to 1. And we said t is equal to 1, then you're at the point 4, comma 1. So let's identify that point here. That's 4 comma 1. So when t is equal to 1, I would be sitting at this point. So if I graph this line over here, I should see that line being tangent at this point. So let's take a look. Y is equal to 1 minus 3 halves x minus 4. Tangent. Nice. All right. Tangent parabola. Y equals the same thing as a tangent line, and then we tack on the stuff that makes it look like a parabola, which is 3/4. It's 3/2 divided by 2. That's how we got 3/4, right? X minus 4, and this one you have to square. So it's tangent to that curve, meaning it looks like that curve very close to it. It doesn't mean that that's where the vertex is. That just means the parabola is going to be touching that curve. So we're going to be, later on, we're going to be dealing with what's called tangent circles. So I kind of want us to kind of get used to tangent things. And tangent just means not that it touches at exactly one point, but whatever shape that you're tangenting to, the graph looks the same near that point. Okay? So that's what we have. Any questions? This is a nice graph. Let's put it in our notes. And you got the feel for the derivatives, yeah? So remember that this is your parametric curve, x of t, comma y of t. This is your tangent line. This is your tangent parabola. And this is your point. When t is equal to 1. Okay. So in calculus, we took derivatives. We also took integrals, and then we applied integrals. We're going to do different kind of integrals later on, but one of the calculus things they want us to cover here is the area under the curve. Area under the curve. So let's talk about the area under the curve. I'll try to type when I can, because I know my handwriting sucks. Well, after a while, I'd like to think that people start to understand what I'm writing. Like if you look at this, what the hell is that? Yeah. So if you understand every other letter and you know enough of the calculus vocabulary to be able to make up the word, you know that this is tangent, not target or not target. And what's this? Yeah. Okay. Well, I asked my class, towards the end of the semester, you guys used to my handwriting yet? A lot of them said no. Oh well. Area under the curve. So that's when you first got introduced to integrals, and I think this is towards the tail end of the Calc 1 and some Calc 2 stuff. So you have y is equal to f of x, some generic function, and then you have points A and B. And then you took this, you took rectangles, and you took areas of the rectangles, base times height, and then you added up a whole bunch of them, and then you make the rectangles thinner and thinner and thinner, and then infinitely thin becomes an integral. And so without going through the whole Riemann sum process, the area here is simply equal to the integral from a to b of your function f of x dx. So now our task with parametric equations is to translate our x of t, y of t into dealing with this, being able to find the area under the curve. So let's see. Let's see if we can find the relationship between things. You have y is equal to f of x, and then we have our functions, our x of t, y of t. They're functions of t. That's your parametric equation functions. So somehow we need to rewrite this or rephrase this into something with t's in it. Well, if y is equal to f of x, then it looks like that part seems pretty easy, that y is just going to be f of x, so this is going to be y of t. Now, the tricky part is your x. X is a function of t. How am I going to find the dx out of that? So if I write it like maybe like this, x is equal to x of t, I could take what's called a differential and say dx is equal to x prime of t dt. So if I take that differential and replace that with dx, then I'll have my formula. Now, since this f of x becomes y of t, it's going to be a function of t. And now I compensate for my dx with this change of variable. Now I have something in terms of t. So I think that's all there is to it. Well, except maybe the limits need to change as limits of t. So let me just show you the formula that they have in the book. Uh-oh, it's not going to fit. Oh, no. Oh, I could shrink it, but I can just put it in the next page. Can you guys see? Should I put it in the next page? It's basically here. The only tricky part is knowing how to deal with the limits here. Aside from just plugging in the formula, the limits, since these are x values, the limits change to x values when you put in the x and the y values of things. So you have to figure out what t value goes into the x function to get a and b. So those are the t values that you're going to want to put into your new integral as a function of t. So the integral now goes from a function of x, where your x is your independent variable, and it changes into a function of t with the appropriate substitutions. Okay? So I think that would be the tricky part, the trickiest part when you're finding the area under the curve. Let's see. Do I have any examples of this? Oh, here's some examples. Let's try number 32 or 33. Okay, either case, we have to find out some weird stuff. So, which one should we do? 32. All right, find the area enclosed by the curve. X is equal to t squared minus t, or sorry, t squared minus 2t, and then y is equal to the square root of t, and the y-axis. So I have to figure out where it crosses the y-axis. When I'm talking about an axis, x or y, one of the variables is equal to 0, right? So it crosses the y-axis, which variable is equal to 0? X is equal to 0. So that might give me a hint as to what values of t to look for. So x-axis or y-axis is not the x-axis, so this is throwing me off even more. This probably wasn't a good example to start with, but this looks like the area bounded by the curve and the y-axis. So I'm assuming the curve does something and it's going to cross the y-axis a couple of times, hopefully no more than twice so that I won't get mixed up. And then I want to find this area. Okay? So the first thing to do is figure out where to go from where to where, and how this thing might look like. All right, so we'll let x-axis or y-axis, sorry. The y-axis, we're going to let x equal to 0. Is that what you guys said? Let x equal 0. So if we let x equal 0, we have 0 is equal to t squared minus 2t. Okay, it looks like it's going to work out. Factor out a t. And then I have t is equal to 0 and t is equal to 2. So when t is equal to 0, the x is equal to 0 and the y is something. When t is equal to 2, the x is equal to 0 and the y is something else. All right, let's figure out what those points are so I can draw my graph a little bit better. So when t is equal to 0, we know that x is equal to 0 because that's how we solve for it. But y is equal to, well, it's also equal to 0, it looks like. When t is equal to, what's the other one, 2, x is equal to 0 again, because again, that's how we found it. Y is equal to, well, square root of 2, whatever that is. What is it, 1 point something? Yeah. Okay. So I have a couple of points at least now. I can adjust my graph to say that this is 0, 0, that's the first point right here, and 0, comma, square root of 2. I guess just out of curiosity, I might be interested in figuring out whether this is on the left side or on the right side of the graph. I just kind of randomly drew this on the right side because that would make our computation a little bit easier. But let's see. How can I find out whether this is on the left side or the right side of the graph? Whether the graph is on the left or the right? Any ideas?
Can we try to figure out where x is equal to 1?
When t is equal to 1. So when t equals 1, looks like it's a number between 0 and 2. And this, for all intents and purposes, all the stuff that we're going to be dealing with are nice and continuous and stuff like that. So if this is, if t is going to give an x value that's positive or negative, that's what we're going to be concerned about. Okay, so when t is equal to 1, what happens to x? Is it positive or negative? Negative. Do we have a number? Negative what? Negative 1. So, and y should be a number between 0 and square root of 2, I hope. Y is also equal to 1 in this case. So we got 1 and negative 1 for x and 1 positive 1 for y. So it looks like our graph does go on the negative side. Now, I don't know if this is the vertex. I just kind of drew it like that. It might go past this, or it doesn't matter at this point, but I know that this is how it's going to look like for now. All right? So, we have these limits. We were going to use this as limits for our integral, but now the integral that we just talked about over here is an integral between the graph and the x-axis, above the x-axis. So now I'm going to have to use some sort of calculus 1 and 2, to try to figure out how to find this graph. And then translate that calculus 2 into the calculus 3 type integral when we're looking for the area under the curve. So if I'm looking at this from the calculus 2 point of view, and you had this curve over here, I might want to call that curve x is equal to some function of y, because now it's not a function of x anymore, vertical line test and business, but it is a function of y. So if I look at it sideways, if you tilt your head to the right, you'll see how it looks. You have to tilt it to the right, not left. If you tilt it to the left, it'll be upside down. Tilt your head to the right. All right, so if you tilt your head to the right, you see that this is actually below the axis, right? So we have another issue that this is below the axis. So let's say you were doing a Calc 2 problem and you were able to write this as x is a function of y. Then you would say that my integral, the area of this, is going to be my integral from 0 to square root of 2 of g of y dy. What's wrong with this? Well, no, I'm still in calculus 2. This isn't quite correct. What's wrong with this? It should be negative because it's below the x-axis. Or below the x-axis. That means if you turn your head to the right, look at it, it's below the y-axis. So that's why it has to be negative. All right? Now, if we look at this, instead of f of x dx, it's g of y dy. And so it looks like we should treat it the same way, except change some of the variables around. So kind of like that relationship here with the x of t and y of t. I think I want blue for that one. This is x as a function of y, or x as a function of t. So we'll just say x as a function of t. And then now this is the tricky one, the differential, the one that needs to get changed into a dy dx or dy dx dy or dy dt, dx dy dt. Yeah, you know. So here we have y as a function of t. So we want to replace our dy differential as y prime of t dt. And so this is y prime of t dt. All right? So we got our limits for our integration. Oh, no, we don't have our limits for integration. Right now it says 0 to the square root of 2. But those are y values, 0 square root of 2. So we just need to make sure we place them with t values. Okay, let's do it. Let's get this into an integral form. Now our area is going to become the integral, and we have new t limits now. T goes from 0 to 2. And this is going to be an integral with a t in it. We have x of t, t squared minus 2t, times y prime of t. Oh, that's a derivative. We should have done this on the side, but you guys are all experts at taking derivatives. So this is our integral. All the components that we've just discussed are all here. We changed our y is equal to 0 to y is equal to the square root of 2. We changed that since we're not integrating with respect to y anymore. We're integrating with respect to t. We changed that into the appropriate t values. These are the t values that would give me the y is equal to 0 and square root of 2 values. Now I have an integral with respect to t. Oh, it's right here. Just couldn't see it because I didn't put it there yet. No, I forgot. All right. Now, is this an easy integral? Is this integration by parts or some weird substitution or something? Anybody? Yeah, so if you take this and multiply it through, then it becomes just piece by piece integration. Right now it's multiplication. Whenever you see multiplication in the integral, you should be kind of worried a little bit. You might have to do integration by parts or some fancy substitution, or maybe not fancy substitution. But if these are some polynomials or some term-by-term things that you can multiply out, certainly take advantage of that. Because now we'll just take the integral one by one. So let's see. This is a negative from 0 to 2. And if we multiply this out, it'll be 1/2. I need to add 1/2 plus negative 1/2. What is that? 3/2 maybe? And then the 1/2 and the 2 cancel. And I have t times t to the negative 1/2. What's my power? Positive 1/2. That is an easy integral. Just don't forget the negative sign. So I have a 1/2 as a constant. What do you do when you integrate? Add 1 to the power. So that's 5/2 divided by 5/2. Looks like the 2's would cancel there. I'll cancel that in a minute. And then I have t to the 3/2 over 3/2. right, let's see. Cancel, cancel. You got 1/5. T to the 5/2 minus 2/3. T to the 3/2. Going from 0 to 2. 0 is going to go away if I put 0 in there, so I'll just put 2 in. You got 1/5 2 to the 5/2 power minus 3 2/3 2 to the 3/2 power. Doesn't look like I can simplify much after that, so unless you want to put in your calculator and get a decimal approximation, I think we're good. So that's the thing about your homework. I haven't adjusted the date yet. For your homework, sometimes they ask for a numerical value. They ask you to approximate up to like 4 decimal places, which is fine. If they don't ask you to approximate, you have to give the exact answer. The exact answer may have square roots or some weird powers like this that you can't really simplify. So this is where you're going to have to type in your assignment. Okay? All right. How's it going? Remember your calculus? All right. So this one got a little tricky. Like I said, I should have done an example where it's below the x-axis, but here it's along the y-axis, so it got a little tricky for us. But if you carry that same idea, this visual over here, I think, where the f of x becomes x of t, or f of x, sorry, the f of x is a y of t, and then the dx, you take that and take the differential of that, and then replace it with x prime of t dt, then you have a more flexible way of understanding this formula instead of just copying it. Questions? All right. The last type of calculus that we're going to do looks like it's going to be a, what's that called? Arc length. Oh, dang. Right here. Should be. Well, let's make sure. This value here should be positive, right? Let's see. Which calculator to use? I'll use this calculator. So it's a negative, parentheses, 1/5, 2 raised to the (5/2) power minus 2/3, 2 raised to the 3/2 power. What's positive? So looks like it all turned out okay. The thing about the integral setup that I have here in green goes from your integral should always go from lesser value to a greater value. So it goes from 0 to square root of 2. And then we put this negative in front because it's below the x-axis. It's on a negative y level. And so it technically, if we really want to look at it from a calculus point of view, it's really x is equal to 0, that's the y-axis, right? Minus x is equal to whatever this function is, g of y. So technically it's 0 minus g of y. So there's a negative here, but really there's a 0 function in front of that. That gives that negative sign because it's below the x-axis, below the y-axis, below the y-axis. Again, when I say below the y-axis, you're tilting your head to the right, below the y-axis. Might as well get this value down, right? All right. Any other questions? It was a good question. Thanks for the negative sign. Any other questions? All right, let's move on to our arc length. There's a nice story behind this that won't have too much time to talk about. So I'm just going to give you the formula. The idea behind this arc length is just, let's see if I can do a quick recap of the story. You have a curve. When t is equal to a, you're at some point, and when t is equal to b, you're at some other point. And then the curve traces out whatever it traces out. It could be a circle, or it could be whatever other shape that it might be. So the idea behind this is that this is really breaking this down into little pieces. And so if you look at, there should be a picture in your book where they break this down to little pieces, and then they find the straight line distances between each of these little pieces. So they find distances between a couple of points. And the distances they're looking for is a change in x and a change in y. So if you look at the formula for this, if you use Pythagorean's theorem or whatever, the formula for this is going to be the square root of each of these sides squared added together. So each of these dx or delta x and delta y, if you cut them up to small enough pieces, will eventually become the derivative of x and the derivative of y with respect to t. And so that's how they come up with that formula. So that's a quick wrapped up version of this formula, what this is about. But it comes from partitioning into small pieces and making triangles, Pythagorean's theorem, finding the length of each of those line segments, and then doing Riemann sums on them. Okay, aside from that, that story should have been told to you when you were taking Calc 2. I think they did this in Calc 2 some way or another. But instead of parametric equations x of t, y of t, you just have y is equal to f of x. So the story might have been a little bit different, but the idea is that you're breaking it down into these small pieces. All right, let's do an example just so we can get one example done here. Set up an integral that represents the length of the curve. Notice they say set it up. They don't want you to do the integral by hand because it might be a little difficult. So we're just going to set it up, and then you can use your calculator to estimate. So 37, 38, 39, 40. Any one in particular? 39. Got some sine functions in here. Doesn't matter because we're not going to solve it anyways. So all this really boils down to is being able to use a formula. And the components that we want out of the x and y functions are x of t, or dx dt, and dy dt. So our function x is equal to t minus 2 sine t, and our function y is equal to 1 minus 2 cosine t. We want the derivatives of those. Let's call it x prime. A derivative of t is 1. The derivative of sine is positive cosine. So that's one of them. That goes into the x prime. We just wrap it around and square it. Our y prime, derivative of 1 is 0. We got 1 minus 2 cosine t. The derivative of that is, derivative of cosine is positive or negative? Negative sine, so negative and negative. Let's just put a plus there. Say it was once a negative, we cross it out, became positive 2 sine t. Okay, so your arc length L is going to equal to the integral, and these are the t value integrals, the t limits that you want. So we're going to go from 0 to 4 pi, and we're integrating the square root, big square root, and then we're going to take the x prime, 1 minus 2 cosine t, cover that up and square it. And then the other one is 2 sine t squared dt. Now if you do this by hand, you need to expand this and hope that things will cancel. May cancel, may not. So some things are going to simplify a little bit, but in general, you'll have a tough integral with a square root. So this wouldn't be something that I would expect you to be able to do by hand. Which is why they say just plug it in the calculator and get a value. Okay? And that's all there is to it. So the calculus part of this is this whole story of how they partition it. Again, I'm not going to talk about it, so if you just read through the book, you'll see the explanation. I think it's a fairly simple explanation, and it'd be good for you to try to internalize that idea so that this formula wouldn't be so bad to memorize. It's just Pythagorean theorem if you look at this as the sides of the triangle. Questions? All right, I think we're good for today. Next time we're going to jump into polar coordinates. So if you have your calculators, I'll talk about how to put this in your calculator and polar coordinates, and then we'll do some calculus on it too.